uh, the last thing sir was teaching you was, I guess, escape speed and all, है ना? Escape velocity and gravitational potential. ठीक है? So we can start from. Uh,
Your voice is breaking.
voice is breaking. अच्छा, just a minute. ठीक है. Now is it clear? Yes. Don't worry. Most probably it must be some network issue. In a while it will clear out, है ना? अच्छा. So sir told that you have to start with Earth's satellite. ठीक है. Sir has completed your escape velocity concept. So next topic is your Earth's satellites. ठीक है. Now everybody knows, ठीक है, you all of you know that what is a satellite. ठीक है, anybody who can just write a short line or say anything about a satellite. What is a satellite? अच्छा, escape velocity is not done. Escape speed you have not done yet. ठीक है, ठीक है, ठीक है.
No, sir.
Okay, no problem, no problem. Gravitational potential you must have done at least, है ना? Gravitational potential of spherical sphere and shell and all, है ना? ठीक है, ठीक है, ठीक, no problem. ठीक है, it is a small concept, we can do that also. Escape velocity. ठीक है. So you must have heard, ठीक है, that there is a certain threshold of speed. ठीक है, there is a certain. हाँ, ठीक है, ठीक है. I guess my network is lagging a bit, but no problem. ठीक है. Uh, let's come back to escape velocity. So what is escape velocity? Now you must know, you must have heard that rockets which are launched into space need some threshold velocity. They require some minimum amount of velocity to escape the gravitational pull of the Earth. That velocity is called as the escape velocity, is denoted by VE. It is written as V subscript E. So what is VE? It is the minimum velocity required to escape the gravitational pull of Earth from the surface of Earth. Okay. This minimum velocity is called as escape velocity. Very simple thing and a very basic concept, that if you throw something with such a high speed from the surface of the Earth, it is possible that it can escape the gravitational pull, or it can escape the gravitational effect of Earth. Okay, simple thing. What is that minimum velocity? We need to know, we need to calculate. Okay. So how to calculate it? Very easy. You have understood gravitational potential, conservation of energy and all. Okay, so that becomes easy. Now, how to calculate it? Just see. Suppose this is Earth. Okay, this is Earth. Mass of Earth is me. Radius of Earth is re. Let's write it capitally. ठीक है. So this is Earth, mass is me, radius is re. ठीक है, you know the values, that is a different matter. Now what are we trying to do is that on the surface I have a mass of small m. On the surface I have a small m mass, and it is launched, it is thrown in the space. Okay, it is thrown towards infinity with a speed of ve. Okay, that minimum velocity after due to which it leaves the earth pull. Acha, to understand what should be the motion. Okay, the smaller mass will move. Okay, it will move, its speed will be decreasing as it is moving away from the earth. Okay, the velocity of the smaller mass will keep on decreasing. Okay, why? Because of a negative acceleration in the towards the earth direction. Okay, so it moves, and finally when it reaches, suppose this is the
Your
distance.
voice is not audible, sir.
Voice is not audible.
It is audible, sir.
It's audible.
It's audible,
Uh,
sir. It,
it's audible.
everybody, no, no, na, everybody is not facing this problem, है ना? So must be network issue. ठीक है, just wait 2-3 minutes, and it should clear out. ठीक है, don't worry about it. It will clear out. Just wait 2-3 minutes. Simple network issue. See, in the network issue, I can also do nothing. You can also do nothing. ठीक है, so don't worry about it. ठीक है, just try to uh, clear the network, है ना? अच्छा. So where were we? ठीक है. So the smaller mass, ठीक है, I had given it some velocity and it was going towards infinity by its reducing speed. ठीक है, slowly by reducing its speed, it is trying to reach the point of r equal to infinity. ठीक है, that is away from the, ठीक है, beyond r equal to infinity, you know, beyond r equal to infinity there is no gravitational pull of the earth. ठीक है, so if this smaller mass just somehow manages to reach this point, ठीक है, that is r equal to infinity, if it is somehow able to reach this point, है ना, by reducing its speeds gradually, and finally when its velocity becomes zero at infinity, it will have just escaped the pull of the earth. Simple, है कि नहीं, है ना? What is escape velocity? That whenever the velocity of an object, of a particle from launched from the surface of the earth has zero velocity, has zero velocity at r equal to infinity, is called as your escape velocity. Okay, why r equal to infinity means, is understood that from that point onwards the effect of gravitational pull from the earth is zero, it is gone. Okay, and velocity equal to zero means it is just reaching that limit, it is just reaching that r equal to infinity surface, r equal to infinity limit. Okay, so we can say that it is the minimum velocity. Okay, and we have written here in the definition also that escape velocity is the minimum velocity. Okay, the least velocity required. So now see this condition, this point, a point, and let this be b point. Okay, so a point is your initial position, this is your initial condition, and this is your final condition. Okay, between these two positions a and b, all the forces which were acting on it were gravitational only. Okay, it was only gravitational force, and gravitational force is always conservative in nature. Okay, you must have studied this in work energy, that conservative. So gravitational force is a conservative force. Since it is a conservative force, conservation of energy can be applied over here. Okay, acha, if it can be applied over here. Yeah, you can take it. Just ask. Okay. Why ask someone? Ask me. Yeah. I won't bite. Okay. Chalo. है ना? So no problem. If you have anything you want to see before thing or anything, okay, I could have zoomed out also and you could just taken the screenshot of this complete thing. Okay, so I was waiting for that only to just complete the topic so you can take a screenshot as a whole, है ना? ठीक है.
Thank you, sir.
Okay, no problem. ठीक है, so where was I? हाँ, conservation of energy. ठीक है, we are going to write the conservation of energy, है ना? We are going to write energy initial is equal to total energy final. Total mechanical energy initial is equal to total mechanical energy final. Anybody tell me what should be the value of initial kinetic energy? What should be the value of initial kinetic energy? Anybody? You can write it in the chat box also, no problem. Half mv square. Very good. ठीक है. Initial kinetic energy is simple. ठीक है. You are talking about the small m mass, so half mve square will be the initial kinetic energy of the system. ठीक है. Of the object. Yeah. What should be the initial potential energy of the object? This is the situation. A is the initial point. Just tell me what should be the initial potential energy of the object. Yeah, that's it. That's it. ठीक है. Kinetic energy is correct. Now tell me what should be the potential energy of the object. Zero. Mm-hmm. Think. Initially, where is the small m mass? Initially, the small m mass is on the surface of Earth. ठीक है. So if it is on the surface of Earth, let it be any point. You can write the potential energy of small m mass as m into delta v. ठीक है. You must have written like this. The potential energy you must have defined like this in work power energy. ठीक है. M delta V. ठीक है. So now see, potential difference or potential at a point due to Earth is how much? ठीक है. Potential at a someone sorry. हाँ. If someone asks you what is the potential at a point due to Earth, ठीक है. So that point is on the surface of the Earth. So you can write the potential as GME minus GME by RE. This will be the potential on the surface of the Earth. है कि नहीं? So the potential energy in this case will become MVA. This is how you write potential energy. If you multiply the potential of the point with the mass, it converts into potential energy. Simple. ठीक है. So if you have the potential, you must have done the gravitational potential just before this. So the potential energy, initial potential energy can be written as m into g minus g me by r. So this will be the initial potential energy of your small m mass. ठीक है.
So could you please scroll up a bit?
Yeah. Yes. ठीक है.
Excuse me,
Minus.
sir.
Yes.
Also, I did not get how potential energy is m delta v.
How potential energy is m delta v. See, whenever you write potential energy, just you have not done this in this manner, na? Acha, you have done potential. ठीक है. Gravitational potential you have done. Yes.
Yes, sir.
ठीक है. Now just tell me. ठीक है. I'm just going a bit into the flashback what you must have done. That suppose I have masses m1 and m2. ठीक है. Suppose I have masses m1 and m2 and they are at a separation d. Just tell me what is the potential energy between the two masses. Anybody. Yeah, you have not done this. You must have done this. This is basic. Okay, not. Let's make it a point
G
mass.
M1 M2 upon D.
Yes, that's it. Okay, minus G M1 M2 upon D. Very important. Minus should be there. Yes. Minus sign. Okay, don't forget minus sign. है ना? So minus G M1 M2 by D will be the potential energy. अच्छा. Now see. Another way. ठीक है, another way to visualize this thing. ठीक है, to visualize potential energy is what? ठीक है. First of all, just imagine that I have a mass m1, ठीक है, point mass m1, and I have a point A at d distance. So what can you write the potential at this point? Anybody, what will be the potential due to mass m1 at this point? Have you done potential or you have done only potential energy? Because both are same. Okay, if you have not done gravitational potential, doesn't matter.
Your
Okay.
voice was not audible, sir.
Okay, voice is not audible. Acha. Okay, I will try to speak a little
It's
bit
clear,
slowly.
sir.
Yes.
It's audible. You can hear it.
ठीक है, no problem. Just I will speak a bit slow paced, but doesn't matter. ठीक है, let it be. है ना? Just tell me, have you studied gravitational potential energy or have you studied gravitational potential?
So gravitational potential energy.
ठीक है, you have not studied gravitational potential, है ना? Only potential you have not studied.
Are they the same?
Yes, sir.
हाँ, ठीक. Means if you see in terms of physics, they are basically same. ठीक है, there is not much of a difference between them. But ठीक है, you let it be. ठीक है, you have not studied these, so I should not tell you how to go in this. ठीक है, but let it be. ठीक है, don't leave it. Leave potential. ठीक है, don't go by the potential method. ठीक है, simple, let it be. ठीक है, again from the starting. ठीक है, you have not studied potential, so doesn't matter. ठीक है, from the starting again, if the potential energy of 2 point masses is minus gm1 m2 by d, so when I have me and m between at a distance of re from each other, okay, the earth and the smaller mass are at a distance of center to center distance of re from each other, the potential energy of the system can be written as minus gmem by re. Simple. Okay, you must have done this, and at least this you must have done. Potential energy है कि नहीं? Yes, ठीक है ना? So now I guess it is clear how to write potential energy, initial potential energy. ठीक है, I thought you must have done potential also, but doesn't matter. ठीक है, that is not useful over here. ठीक है, it is used in later on chapters, but no need over here. ठीक है, even if you don't know what is potential, if you know what is potential energy, that is also fine. ठीक है, so this was your initial condition. ठीक है, everything about initial, you know the potential energy of the initial, you know the kinetic energy of the initial. ठीक है, now let's come on to the final condition, final position. ठीक है, tell me what is the final kinetic energy? Anybody? This should be easy. What is the kinetic energy?
0.
0. Brilliant. That's okay. I've just said that as it reaches point B, okay, as it reaches point B, yes, and the velocity of the smaller mass becomes zero. Hence, the kinetic energy final will be zero. Simple, as simple as that. Nothing to worry about it. Now, tell me what final potential. Anybody? What should be the final potential energy? Yes, yes. Yes, what should be the final potential energy? Why are you also in confident means underconfident?
So
Tell it in
infinity,
confidence. Yes, it should be
infinity,
infinity. No, zero again. That's it. That's it. Okay, zero. Someone else was also saying zero. Okay, no. Root mgh cannot be the potential energy over it. Na? See, again it is zero. Again it is zero. How it is zero? Just see. This was your initial condition. Okay, m1 m2 masses. Okay, just a detour. Okay, you have m1 m2 masses. Okay, they are at a separation d. Then the potential energy can be written as minus g m1 m2 by d. Okay, till here no problem. Now what I am saying is that the separation between m1 and m2 becomes so large, okay, that it becomes infinity, and our d becomes infinity. And so if d becomes infinity, the potential energy formula is still applicable. Okay, the potential energy formula is still valid. So I will write as g m1 m2 by d. I should have written d, but now the value of d has become infinite. So if you divide anything with infinity, the term tends to, or term becomes zero. The whole answer becomes zero. And yes, something upon infinity is zero. So that is what is happening over here. Hence, at infinite distance, at infinite separation, you should always remember that the potential energy will always be equal to zero. Okay, potential energy will always remain zero at infinite separation. Okay. Acha. Now you have initial and final potential energy. Okay, you have initial and final kinetic energies. So you can apply conservation of energy. What is conservation of energy? Say that kinetic energy initial plus potential energy initial is kinetic final plus potential final. Okay. Replace the values. Just replace the values. You will get a result of escape velocity. How? Just see here. ठीक है, this is extra है ना, don't if you don't want to write it, you can leave this part. ठीक है, or if you want you can write it in a bracket or somewhere. ठीक है, some other space. Don't break the continuity of the that escape velocity. ठीक है. अच्छा, so where was I? हाँ, kinetic energy plus potential energy initial. So initial kinetic energy we calculated half mv square. Initial potential energy we calculate at me by re. This should be equal to 0 plus 0. Okay, this is the equation which I am getting. Okay, from conservation of
Repeat
energy.
Srila Prabhu.
Yeah.
Yes, sir, thank you.
Okay. Acha. Now see, once I have this equation, from here it is easy to calculate the escape velocity. Simple, just rearrange the terms. I have half mv square is equals to gmme by re. M gets cancelled. Ve square comes out to be 2gme by RE. So therefore what I can write here, that escape velocity comes out to be under root of 2gme by RE. This is the value, this is the formula of escape velocity. Okay. For escape velocity from Earth, okay, if you want the escape velocity from the surface of the Earth, है the formula is under root of 2gme, that is mass of Earth, upon re, that is radius of Earth. Okay. And if you change the planet, okay, if you change the planet, the mass and radius will change. Okay, the mass and radius of that planet will be required. Okay, like suppose you want the escape velocity on Mars. Okay, then what will be the formula for that? Under root of 2g mass of Mars upon the radius of Mars. Okay. So this you can see here that this escape velocity is a term which is dependent on the planet and not on the mass itself. Okay. There is no involvement of the mass of the object. Okay. The mass and radius, the properties of planet is required over here. So as you change the planets, your escape velocity will change. Otherwise, it will be constant for a given planet. ठीक है, is it clear? है ना? अच्छा ठीक. अच्छा, so now see, this was escape velocity, one of the representations of escape velocity. ठीक है, we are familiar with a small g representation. ठीक है, we want the answer in small g. ठीक है, that is acceleration due to gravity. We want to introduce small g over here. So what you can do is just see the value of small g. Okay, you know the value of small g can be written as gme by re whole square. Okay, this is the value of in terms of gravitation constant, mass of Earth and radius of Earth. है ना? Re square. है ना? It should be re square. So what you can do is you can write gme by re as GRE. Okay, G times radius of Earth. So you can replace this complete term over here. So the escape velocity has another representation. Okay, the basic is same. Okay, it is just a representation. It is under root of 2GRE. It is under root of 2GRE. That's it. Okay, so whichever is suitable to you, okay, whichever you want, you can remember it. But this is the most widely used, the formula that the under root of 2GRE is the most commonly remembered, easily remembered formula. Okay, because acceleration due to gravity is constant, Okay, it is 9.8 meters per second square approximately. So the values can be calculated easily. Acha, in case of Earth, the escape velocity, okay, for Earth, the escape velocity when you replace the values of g and re over here, okay, radius of Earth, okay, 6,400 kilometers. It is 6,400 kilometers approximately. So when you replace these values over here, the escape velocity comes out to be 11.2 kilometers per second. Okay, this is also a value which you can remember. Okay, it is a very easy thing. Most of the cases you remember that escape velocity of the Earth is 11.2 kilometers per second. Okay, just see how large a speed you need. Every second you need to cover 11 kilometers, around 11 kilometers. Okay, if you attain this much speed, you can escape the boundness of Earth. Okay. So using this escape velocity, okay, the scientists are able to create the rockets and all. Okay, they try to attain this speed so that the rockets and all that satellites reach the outer space. Okay. And so you have to remember these three things. Okay. If you want to remember the first formula, remember it. If you are unable to, definitely remember the second formula at least. Okay. One of the two formulas you need to remember, and the value of velocity. Okay. Acha. Any doubts, anybody? Okay. So let's do a question. Clear है ना? ठीक है. This is the question. Escape speeds at surface. Okay, this is the question that you have a ratio of masses and radii of two planets given to you. Okay, one ratio of masses is 2:3 and ratio of radii is 4:9. So you have to find the value of ratio of escape velocities. Very simple. Just try it yourself once. Okay, then just tell me what should be the answer. Okay, if you are not able to get it, then I will just solve it. Yes, anybody getting answer? Or should I solve? Yes, root 3 is to root 2. Good, 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 good. Nice. Okay, so very basic question. Okay, just write what is given to you and what is known to you. Okay, first of all, ratio of masses is given. Ratio of masses means simple. M1 by M2 is given to us as 2 by 3. Yes, root 3 upon root 2 is the correct answer. Okay, so ratio of masses is given. M1 by M2 is given to us as 2 by 3. And ratio of radii is also given. That is R1 by R2 is given to us as 4 by 9. Simple. Okay. What they are asking is what should be the escape velocity of 1 upon escape velocity of planet second. Okay, this is the ratio which they are asking. So just replace the formula which we know. Okay, that is under root of 2g m1 by r1 upon under root of 2g upon r2. Okay, why I am here using the first formula? Okay, because mass is also given to us. Okay, ratio of mass is given to us. So what we need is the formula which includes mass. Okay, in under root of 2GRE, the second one, okay, there is no mention of mass over there. So I cannot use that formula over there here. Okay, so what I can now simplify this ratio if you simplify this ratio, you can see that 2g and 2g is common, they will cancel out. Okay, this will be under root of m1 r2 upon m2 r1. Okay, this will be the simplified form of the ratio of escape velocities. Okay, yes. Okay. Now see, this is m1 by m2 and this is r2 by r1. Okay, try to see it like this. So under root of m1 by m2 is 2 by 3, m1 by m2 is 2 by 3, and r2 by r1 is reverse of this. Okay, it is the reverse of this, that is 9 by 4. Okay, so when you solve this, you can see here that it comes out to be under root of 3 by 2. This is the final result. That if you write it in terms of ratio like this, it will be root 3 is to root 2. So this will be the result you will be getting. Okay. Hope it is clear. Yes. And now this is the complete question. Okay. Simple question. Okay. Very easy, basic question. Okay. Achha. Now let's see another question. Okay, this is a question that suppose you have a satellite. Okay, suppose a satellite is launched with a speed of 3 times escape velocity from the surface of the Earth. Then what will be its interstellar speed? Okay, now for this you need to understand. For this you need to understand what is the meaning of interstellar speed. Okay, just try to understand. It is simple, it is basic thing. Okay, you must have seen that interstellar movie and all. In that you must have seen that when air spaceships, okay, in the movie, when the spaceship leaves the earth's atmosphere or any planet's gravitational
So
pull, in
can you
fact,
please scroll up?
yes,
So my network had
no problem.
so my network was lost.
No problem. Okay, so what I was saying, that in interstellar, you must have seen that whenever they try to leave, no problem. Okay. So whenever they try to leave the any planet, okay, any gravitational pull of any planet, okay, they try to keep some velocity after leaving the planet. Okay, you must have seen that uh, whenever they tried to leave some planet, they had some velocity even after leaving the planet. Okay, that leaving the gravitational pull of that planet, that velocity is called as interstellar speed. And in fact, for that matter, let me just simplify it. Suppose this is a planet. Okay, just imagine the universe. Okay, and there is a small planet on the in the universe. Just for example, let this be the point till where you can feel that the gravitational pull of the planet is there. Okay, it will be a big spherical surface. Okay, it will be big like this, covering it overall, just on the right hand side. Okay, this will be the limit. Okay, so for this planet, this distance is r equal to infinity. This is r equal to infinity. Okay, so from the center to this r equal to infinity distance, this region has gravitational pull. This is gravitational area. Gravitational pull is there. Okay, but beyond this, if something is there, beyond this line, if something is there, it won't have any gravitational effect of this planet. It won't feel any gravitational effect of this planet. Okay. This region, this complete region beyond this point, okay, is called as interstellar space. Interstellar space. Anything beyond the gravitational capacity of a planet is called as interstellar space. Okay, it can be any planet. You can take Mars, Pluto, Neptune, any planet. Okay, beyond the gravitational pull of that planet, there will be some space, and that space is called as interstellar space. Okay, now just imagine I have a object kept on the surface and I have launched it with some escape velocity, some velocity. Okay, not escape velocity, some velocity. That large, okay, that even when it reaches infinity, it has some different velocity. Okay, it is still moving with some different velocity. So it has, once this mass has reached r equal to infinity, okay, the gravitational pull is over. Okay, it has entered interstellar space, but now it has some velocity. This velocity in interstellar space is called as interstellar speed. Simple. Okay, the velocity of a particle in interstellar space is called as interstellar speed. And now what will happen, just try to imagine there is no gravitational pull, there is no kind of force acting on the mass in interstellar space. So what will happen, the particle will keep on moving with the same constant velocity. V dash will become now constant, the new velocity will become constant. Okay, so since there is no force, nothing acting on it, okay, the force has become constant, the velocity has become constant. The force has become zero, the velocity has become constant. Since velocity is constant, it will keep on moving in interstellar space with the v dash velocity. Okay, so this is what is called as interstellar speed. Okay, these are few terms used in questions. Okay, just to confuse you. Okay, basically when they are asking what is the interstellar speed, they are asking you what is the velocity when it just crosses the r equal to infinity line. That's it. Okay, you don't have to worry about anything else. They are just saying that what should be the speed when it crosses the r equal to infinity line. That's it. This is what we have to understand. Okay, so if you are not getting interstellar space and all, let it be. No one is asking what is interstellar space. Okay, so this is the situation which we have, that the particle is thrown with 3 times the escape velocity. Okay, this is a point, this is b point, and at a point my satellite has a velocity of 3 times escape velocity, 3v, and when it reaches b point, it will have some velocity v dash. Okay, let it be v dash, or if you want we can write it as vb, no matter. Okay, that will simplify things. So let's write it as vb. Okay, it will be better, no problem. vb. Okay, the velocity at b point is called as interstellar speed, and this is what they are asking us. Okay, so how to calculate this? Okay, this is the reason, this kind of question is the reason which why I calculated conservation of energy, why I applied conservation of energy in the derivation of escape velocity, because here the conservation of energy will be applicable. Okay, you won't be able to apply any of the formula. Okay, what you have to apply here is conservation of energy. Okay, you have to apply conservation of energy over here. Okay, again a point is your initial point, b point is your final point. So again just tell me what should I write the initial kinetic energy. Anybody, what should be the initial kinetic energy in this case? Okay, assume the mass of the satellite to be small m and mass of earth to be me. ठीक है, radius to be RE, this radius of Earth planet to be RE. What should be the initial kinetic energy of this satellite? Yes, 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 yes. ठीक है, half m 3ve whole square. ठीक है, half m 3ve whole square will be the kinetic energy. ठीक है, that's correct, that's correct. So it will be 9/2 mve square. ठीक है, it will be 9/2 mve square. अच्छा, initial potential energy if you write, ठीक है, the initial potential energy will be same as what we had in the of escape velocity, that is minus gmme by re. ठीक है, this won't change because it is on the surface of the earth, so potential energy won't change. ठीक है, because the separation between the centers is re only. ठीक है, that won't change. अच्छा, now kinetic energy final, if I'm talking about, that is at point B. Final condition is point B. So at final position, if you write the kinetic energy, it will be half m vb square. Okay, it will be half m vb square, because at B point it has some velocity, so it has some kinetic energy. Simple as that. We have to find this vb only. Okay, we have to find this velocity at B only, and the potential energy final will be 0. ठीक है, I already told you that whenever your distance r becomes infinity, your potential energy becomes 0 for this position, for this point. ठीक है, अच्छा, now what we can write, initial kinetic plus initial potential is equals to final kinetic plus final potential. Simple. So I can write half m 9/2 mve square minus gmme by re is equals to half mvb square plus 0. ठीक है, now this m will get cancelled out, no problem. ठीक है, just do one thing, that is replace the value of escape velocity. ठीक है, we have calculated escape velocity as 2g me by re. ठीक है, just replace this over here. ठीक है, you know this is the formula, this is valid. ठीक है, that is why they are saying that the velocity is 3 times escape velocity. They have given you a reference to write the velocity. That 11.2 meters per second, kilometers per second is the escape velocity. So 3 times that. ठीक है, 33.6 kilometers per second is the speed which I have given. Yeah, so that is why I am replacing this over here. ठीक है, so once I replace this, I have 9/2 2gme by re minus gme by re is equals to vb square by 2. Okay, so this 2 and 2 gets cancelled. 9 minus 1 is 8 gme by re. This is equal to vb square by 2. Just take rearrange this and take under root both the sides. Okay, so you will have under root of 8 2gme by re is equals to vb. ठीक है, why I have written it like this, because see, under root of this, ठीक है, under root of this will again become escape velocity. ठीक है, under root of 2g me by re will again become your escape velocity only. So what I can write is, it is under root of 8 times v escape is equal. Therefore you can say that the velocity at B point, ठीक है, velocity at B point or interstellar speed comes out to be 2 root 2 v escape. Root 8 is 2 root 2. ठीक है, is it clear? This is the complete calculation. ठीक है, someone's mic is unmuted, just mute it. ठीक है, any doubt in this, anybody? Yes. ठीक है जी, just write this.
Excuse me, sir.
Yes.
Sir, you did not bring that 2 at GME upon RE.
Where?
Uh, sir,
This one
sir,
line.
yes, sir.
It is GME upon RE.
Yes,
I
yes,
replaced
sir.
GME upon RE. No? See, here it is V square. Okay, so I squared this first. V square will be how much? It will be 2 GME upon RE only. Okay, so I replaced this complete term over there.
Sir, no, I am saying that you did not shift that 2 for GME upon RE.
The right one GME upon RE.
Yes, sir.
There is no 2 in initial potential energy. Na? This is representing initial potential energy. Okay, so there is no 2 in that. So I cannot introduce from somewhere. And this thing is representing your initial potential energy, not some formula. Okay, so I cannot just replace 2 over there. Okay, 2 this formula will be replaced on V square only. That's it. I'm just replacing the value of V. Okay, escape velocity. I'm not replacing any other terms. Got this?
Okay.
Okay, so that is representing escape velocity. So that can be replaced. ठीक है. Hope everybody has written this, yeah. Okay, so now let's move on. This was a complete escape velocity. Okay, everything about escape velocity is done. You can do questions based on it. Okay, variations can be there, ratios will be changed. Everything you can do. Okay, once you know interstellar speed and all. Okay, basic concept is there in your mind. Okay, now let's move on to Earth's satellite. Okay, Earth satellite. Okay, so initially I had asked that what is a satellite. So one of you had written that where did it go? Acha, you deleted it. Okay, no problem. Okay, so I will tell you what is satellite because we don't have much time. So satellite is just an object. Okay, it is a object orbiting a large planet or something. Okay, a large body is called as a satellite. Okay, a small body orbiting a very large body, comparatively large body, is called as a satellite. Okay? Like the moon is orbiting Earth, so it is a satellite. Okay? The different moons of other planets will be satellite. Okay? The man-made satellite which we have sent in space, okay, for our convenience, telecommunications and all. Okay? They are satellites. है ना? Now you can ask, sir, why planet is not a satellite of the sun? Okay, we cannot say planet as a satellite of the sun because why? Although they are orbiting the sun, but their masses are comparable. Okay, their masses are not their masses are not having a very large difference. Okay, their masses can be compared, and so not very much comparable, but still they are comparable. Okay, planets are very large, satellites are smaller in size. Okay, they are small objects. Okay, very small object compared to planet. So satellite is something which revolves around small objects which revolve around fixed orbit around a planet or any other thing. Okay, they are satellites. Acha. We uh, basically we in this topic we have to study about the motion of a satellite. Okay, whether it be man-made or whether it be natural. Okay, you know there are two types of satellite. One is natural, one is man-made. Natural is moon, man-made is the satellites which we send in space. ठीक है, ISS and all international space stations and all are man-made satellites. ठीक है, so that is a different thing. Nobody asks you. That is basic. You know that. ठीक है. What we have to study in this is how the path, how the motion of the satellite is defined. ठीक है, what are the things governing the velocity of a satellite? What are the things governing the energy of a satellite? ठीक है, these are the things we will study over here. So Earth satellite, ठीक है, simple thing. Let's see. First of all, we need a Earth. ठीक है, to study the Earth satellite, we have a Earth. This is my Earth. This is radius of Earth. This is mass of Earth. Okay. Now, from a h height, from a height h from the surface of the Earth, okay, there is a satellite constantly orbiting in a circular path. Okay, there is a satellite which is constantly orbiting the Earth in a circular path like this, from at a h height from the surface of the Earth. Okay. Now, if it is the satellite is orbiting the Earth, it must be having some velocity. It must be having some kind of velocity uh, along the circular orbit. Okay, you know it needs some velocity to keep moving in a circular path. Okay. Now we have to find the formula for this velocity. Okay, we need to calculate the formula for the velocity of a satellite at a height h from the surface of the Earth. Okay, so how we can do that? It is very simple. Okay, consider the mass of the satellite to be small m. Now, if it is moving in a circular path, okay, if it is moving in a circular path, you all can see that a gravitational force will be acting on the satellite towards the center of the Earth. Okay, there will be a gravitational force acting towards the center of the Earth on the satellite. Simple. Okay. Acha. Now you can also observe this, that as the satellite moves forward, the gravitational force is directed always towards the center, wherever it be. Okay, the gravitational force is always towards the center of the circular motion. Okay, so if this gravitational force is always directed towards the center of the circular motion, I can say that my gravitational force on the satellite is equal to the centripetal force of the circular motion. Why? Because it is always directed towards the center of the circular motion. That is the center of the Earth. Okay. Now, what will be the value of gravitational force? Simple. Gravitational force is G M me upon Re whole square. Simple. Okay, this is the formula, you know, Newton's law of gravitation. Okay, Gm1 m2 by d square. So Gm me by Re whole square. This should be equal to the centripetal force. Okay, if you remember circular motion, the centripetal force formula is mv square by r. Okay, mv square by r. Achha, sorry. Just a minute. This r, this distance which I am talking about is this. Okay, this complete distance is r, or you can say d square. Let's write it as d square, not r. Okay. So here, if you see the value of d can be written as re plus h. Okay, till here it is re, till the surface it is radius of Earth, and beyond that it is height h. So re plus h is the total distance between the two centers. Okay, it is the distance between the center of Earth and the center of satellite. That is re plus h. Acha. We can replace that later on, no problem. Acha, centripetal force if we are talking, okay, formula is mv square by again r. Okay, r is the radius of this circular path. Okay, circular path of the satellite. So radius of circular path is d. Okay, it is d. So here if you simplify it, okay, you get v square is equals to g me by d. Okay, now you can do what? You can replace the value of d. Okay, d can be replaced as g me upon re plus h. Okay, so from here you get the velocity of a satellite in an orbit at height h. The velocity of a satellite in a orbit at height h is under root of g me upon re plus h. This is the formula for the formula for the speed of a satellite in an orbit at a height h from the surface of Earth. Okay. Now, what does this velocity represent? What does this velocity mean? That the satellite, if it wants to remain in this orbit, okay, if the satellite wants to remain in this orbit, it should have exactly this much amount of velocity. Okay, suppose for example, okay, don't take it as a value. Okay, just I'm writing for example that suppose this velocity comes out to be 10 kilometers per second. Okay, just an example I'm saying. Okay, it can be anything. Okay, it can be 9 meters per second also. It can be anything. And just for example, if it should be 10 kilometers per second, so if the satellite wants to remain in this orbit only, okay, its velocity should be exactly equal to 10 kilometers per second. Okay, if its velocity is more than this, then its orbit will be outside. Okay, it will be more further away from the surface. If its velocity is less than this, its orbit will be nearer to the surface. Okay, so for a satellite to revolve in a given orbit, the value of velocity should be a given constant. It should come out to be a specific value. Okay, so this is the meaning of the orbital velocity. This is called as orbital velocity. Okay, that for a particular orbit, any amount of satellite you send in that orbit, suppose two satellites over here more, okay, m1 and m2, more two satellites would have been on this orbit, their velocities will also be equal to this 10 only. Okay, their velocity should also be 10 and 10 only to remain in that orbit. Okay, that is why this velocity which we have calculated is also called as orbital velocity. Orbital velocity, also denoted as VO. Okay, not this VO, let it be orbital velocity. Okay, what is the orbital velocity? The velocity required for the satellite to stay in that orbit, in that particular orbit, is orbital velocity. Okay, any doubt in this? Simple thing. Okay, very basic. Okay, so if you want you can write it. ठीक है, guessing you must have written on here. Acha. Now see the orbital velocity. Okay, orbital velocity can achieve a minimum value. Okay, there is a minimum value. The minimum value of orbital velocity. The minimum value of orbital velocity is denoted as V naught. Okay, the minimum value of orbital velocity is denoted as V naught, and that velocity can be written when h becomes equal to 0. Okay, because you can see here that you cannot form an orbit inside the surface of the earth. you cannot form an orbit inside the surface of the earth. Simple as that. Okay. So the smallest orbit, okay, smallest radius of the orbit possible is that if the satellite is just circling on the surface, is just orbiting on the surface of the earth. Okay. So that means the smallest value of d, you can say the smallest value of d which can be attained is equal to re, where h becomes equal to 0. Okay. So as and when I say that h becomes equal to 0, the formula of orbital velocity can be calculated. You can replace the h equal to 0 over here. Okay. As you replace it over here, velocity VO, orbital velocity, minimum orbital velocity becomes under root of g me upon r e. Okay. Minimum orbital velocity becomes g me upon r e. Again, okay, if you want, you can remember this. Again, it can be represented in the form of small g also. How? Under root of g r e. Okay, we have done this replacement in escape velocity also. Okay, so I am directly writing over here that under root of g me upon re can be replaced as g re also. Okay, so you can see that the orbital velocity comes out to be equal to under root of g r e. Okay, so this is another formula which you have to remember. Now there is a connection between escape velocity and orbital velocity. You can see that. Okay, there is a connection between escape and orbital velocity. If you write just we can write it as a note. Okay, that escape velocity came out to be what? Escape velocity came out to be 2 GRE. Okay, it came out to be 2 GRE. And minimum orbital velocity came out to be under root of GRE. Okay, under root of GRE. So you can see here that this term can be completely replaced as V orbital. So this creates a relation between escape velocity and minimum orbital velocity, that escape velocity is root 2 times minimum orbital velocity. Okay, this is the result which you have to remember. Okay, hope it is clear. Yes. Any doubts, anybody? ठीक है. And a basic thing, these are just circular motion things and nothing new. Okay, almost you can say that it is circular motion only, just in gravitation. Okay, like this. Acha. Another term which we use is time period. Time period of a satellite is very important. Okay, because we need to know whether the satellite is a geostationary satellite or not. Okay, you must be knowing what is a geostationary satellite. Geostationary satellite is a satellite which rotates with the Earth. The rotational speed of the Earth and of that satellite is same, or the time period of that satellite is 24 hours. Okay, it is very simple. You know that your Earth completes one circular motion in 24 hours. So if a satellite also completes a circular motion in 24 hours, that will appear to be stationary on Earth. That is why it is called as geostationary satellite. Okay, these are basic terms you must be knowing, but we will do that later on also. No need to worry about it. Okay. So हाँ, that is also true. ठीक है, that is also the same thing. ठीक है, just different representation. ठीक है, that is the same thing. अच्छा, now let's come to time period. ठीक है, so how to calculate time period of a satellite revolving at a height h from the surface of the Earth? So simple. ठीक है, you know the formula. It is 2 pi r by v. Simple. ठीक है, this is the formula for time period of a circular path. ठीक है, circular motion. ठीक है. अच्छा, what is 2 pi r? R is in this case d equal to d, that is re plus h. ठीक है, it is re plus h, है ना. and velocity we have just calculated the formula over here, this orbital velocity, this complete thing, okay, under root of g me upon re plus h. So this can be replaced over here, g me upon re plus h, okay. So if you reduce it, okay, if you simplify it, this will be 2 pi re plus h raised to power 3 by 2 upon under root of gme. Okay, this is the final result, or you can say you don't have to remember this, take a time period, but this is the final result of a time period. Now what is important over here is that your time period in this case comes out to be proportional to, okay, proportionality is important over here. See, 2 pi is constant, under root of gme is constant. The only variable which you have, the only variable which you have here is re plus h raised to power 3 by 2. Okay, re plus h raised to power 3 by 2 is the variable here. So time period will be directly proportional to re plus h raised to power 3 by 2. This is a very important relation. ठीक है, I guess you have not done Kepler's law till now. ठीक है, so in Kepler's law you will see that why this time period proportional to this is very important. ठीक है, for now just try to remember this, that time period is proportional to re plus h raised to power 3 by 2. ठीक है, और in other manner you can say that t square is proportional to re plus h whole cube. ठीक है, re plus h whole cube, same thing, I just squared both the sides. ठीक है, doesn't matter, है ना, whichever you easier to remember, whichever is easier for you, just try to remember that. ठीक है, for now. अच्छा, so this is the motion of the satellite. This is about the velocity and the time period. ठीक है, now let's move on to the energy of a satellite. ठीक है, just try to keep up with me. ठीक है, I need to complete this at least satellite today. ठीक है, so let's move on to energy of a satellite. ठीक है, so energy of a satellite. ठीक है, so energy of a satellite, what is energy of a satellite? Energy of a satellite means total mechanical energy of the satellite we are talking about. ठीक है, I want to calculate the total mechanical energy of my satellite. So total mechanical energy of the satellite can be written as potential energy plus kinetic energy. Simple. ठीक है, potential energy plus kinetic energy of the satellite. ठीक है, now just try to see this diagram. ठीक है, this diagram which we had drawn over here. ठीक है, forget everything else. This all is extra. It doesn't matter. Now see this. When it is orbiting at a radius at a height h, ठीक है, it is having some kinetic energy. ठीक है, what is the kinetic energy? It is half m v orbital square. ठीक है, orbital velocity whole square. And we have calculated the formula for that. And if you see the potential energy, just let me write here just for a reference. ठीक है, that potential energy between satellite and earth can be written as minus gmme by re plus h. ठीक है, I will write this in the section also, energy section also. So this is the potential energy, direct formula है ना, re plus h, that's it. So what we have here is the potential energy of the satellite can be written as minus gmme by re plus h. ठीक है, minus gmme plus by re plus h, and kinetic energy is equal to, kinetic energy can be written as half m v square, v orbital square in this case. ठीक है, now what is v orbital square? We have written under root of g me upon re as the re plus h as the orbital velocity whole square. This will be the kinetic energy of the satellite. ठीक है. Now what you can do, you can just replace these two terms over here, ठीक है, the kinetic energy and potential energy over here. So the total mechanical energy comes out to be minus g me m by re plus h plus half m g me upon re plus h. ठीक है. So here you can see that this complete term is common. ठीक है, this complete term is common, so you can take it out as common and simplify this. ठीक है, you can simplify this total mechanical energy. So total energy can be written as minus 1 by 2 g me upon re plus h. Total mechanical energy can be written as minus half g me upon re plus h. ठीक है. So this is a result which if you can remember, just remember it, not very important. ठीक है, you can write it anytime, it is very simple. ठीक है, it is just like the formula of potential energy but multiplied with minus half, that's it. ठीक है. So this creates a very important result also. ठीक है, what I just said, you can just take a note also over here, that total energy of a satellite can be written as potential energy by 2. ठीक है, see, this is the potential energy of the satellite, this is the potential energy of the satellite. If you divide it by 2, basically you will be having the same formula as total energy. ठीक है, so total energy can be written as potential energy by 2, है ना. And if you are talking about kinetic energy, ठीक है, so just see the formula for kinetic energy over here, see this. ठीक है, this is the formula for kinetic energy. You can write this as negative of kinetic energy. ठीक है, if you just multiply kinetic energy with a minus sign, you will be having this formula only, exactly this formula. ठीक है, so this is a very important result for any satellite. ठीक है, for a given satellite, if it is orbiting the earth at any height, ठीक है, irrespective of height and all, the total energy it has, ठीक है, the total energy it contains is either equal to potential energy by 2. ठीक है, it can be calculated as the half of the potential energy it contains, or the negative of kinetic energy it has. ठीक है, this is how you can calculate the total energy, है ना. So just for an example, okay, I can write that if a satellite has 30 joules of kinetic energy, then what is its potential energy and total energy. ठीक है, this is the question. Suppose, ठीक है, that you have been given only the kinetic energy as 30 joules, and they have asked you what is the potential energy and the total energy of the satellite. ठीक है, no other information is given, no other. ठीक है, it won't be given, है ना. So simple, just if you remember this note, ठीक है, so what you can write, total energy is what, negative of kinetic energy. ठीक है, so just replace the negative of kinetic energy over here, that is minus of 30 joule. This is my total energy, है ना. What about potential energy? Potential energy by 2 is equal to minus kinetic energy, so potential energy can be written as minus 2 times kinetic energy. So again replace kinetic energy as 30 over here, so potential energy will come out to be minus 60 joules. So you have the potential, you have the total energy without knowing anything about the satellite. You just know the kinetic energy, है ना. You don't know any other information, at what height it is, at what speed it is moving, and anything. ठीक है, you don't even know the mass of the satellite, but you can tell everything about its energy. This is the uniqueness of a satellite. ठीक है, this is the important feature of a satellite, that you can predict the energy, you can calculate the energy, any kind of energy of a satellite. ठीक है, if you have been given Okay, so this is a so this is your energy of a satellite. Okay, I guess everybody is getting this, है ना? Because I am moving a bit fast. ठीक है, because time is not there. ठीक है, but easy things, easy topics. ठीक है, you can understand it easily. अच्छा, next geostationary satellites. ठीक है, next is geostationary satellites. Geostationary.
Just scroll up.
Yeah. ठीक है, अच्छा, geostationary satellites. I just told you what are geostationary satellites. ठीक है, geostationary satellites can be written like this, that satellites which appear stationary to an observer on the earth. Stationary to an observer on the earth. That means whichever time you go out and try to observe, you try to see where the satellite is, it will always be in that location only. It won't move anywhere. That kind of a satellite is called as geostationary satellite. Hello. Okay, so sorry, there was a call coming. Okay, so there was a geostationary satellite. Huh. So what is a geostationary satellite? That which appears stationary to an observer on the Earth. That means basically what we have is that the time period of the satellite is equal. Okay, time period of the satellite, you can write sat. Time period of the satellite is equal to the time period of Earth. Okay, time period of rotation of Earth is equal to the time period of the satellite, because the angle rotated by Earth in one time period is 360 degrees, and if a satellite also rotates the same angle in the same time, then it will appear to be stationary to Earth. Okay, it is just like linear motion. Okay, suppose you have two cars and they are moving with the same speed. Okay, so if they are moving with the same speed, you ask A about B, so A will say that B is at rest, and if you ask B, then B will say that A is at rest. Relative motion. Okay, so in this case also, if Earth is rotating with some angular velocity, and at the same time a satellite is also rotating with the same angular velocity but at a different location, okay, then to Earth, with respect to Earth, this satellite will be at rest. Okay, this is just a side explanation. Okay, this is just for easy understanding. So if the angular velocities are same, their time periods will also be equal to will be equal. Okay, their time periods will also be same. Now, if their time periods are same, and I know the time period of Earth, so if the time period of satellite becomes equal to 24 hours, I can safely say that the satellite will be a geostationary satellite. Okay, it will be a geostationary satellite. Now, if I have the time period as 24 hours, I can use my time period formula, which we have just calculated over here. This formula. Okay, you don't have to remember it. Not a very important thing. You just have to remember this relation. Questions will be asked on that. This is just a derivation. Okay. So what I can write is that time period of satellite is 2 pi re plus h raised to power 3 by 2 upon under root gme. This should be equal to 24 hours. Okay, this should be equal to 24 hours. Now see, 2 pi is constant, under root gme is constant, radius of earth is constant. Only the variable which is there is the height. Okay, that is height from the surface of the earth. So if you calculate this value of h, because now the time period is constant, time period is fixed, so the value of h will come out to be a constant value. Okay. For a geostationary satellite, the value of h on putting all the values and calculating it, okay, the value of h comes out to be approximately 35,900 kilometers, approximately. Okay, you can approximate it to 36,000 kilometers. Okay, it is one and the same, not much of a difference. Okay, it is already approximate value, so you can make it 36,000 for easy remembering. Okay, just you can write 36,000 kilometers approx. Okay, so approximately for a satellite to become geostationary, the height at which it should revolve is 36,000 kilometers. Okay, is it clear? Any doubt in any of these things which I have done? Okay. Okay, so this was your satellite. Okay, your satellite is done. Your Kepler's law are left, so that most probably sir will do it in the next class, or if he is still unwell. Okay, tomorrow only you have a class, I guess. So if he is still unwell, so most probably I will only take. So that's it for today. That's it. Thank you. If you want, you can zoom out and you can write this. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you.